Hi everyone, and welcome to the first of two videos going through some past exam questions on the topic of atomic structure. The first question is a definition. These definitions come up quite a bit. We need to get them spot on really. It's worth 3 marks, which is easy marks if you can learn the definition. This is something that wants to be automatic for you. So the definition of relative atomic mass is that it's the weighted mean mass of an atom and then its relative atomic mass. What is it relative to? So the weighted mean mass of an atom compared to 1/12 of the mass of an atom of carbon-12. Carbon-12 is the reference isotope that everything is compared to. And we talk about the weighted mean mass because we have to take account the different isotopes. And the weighted mean means that we're going to take into account the different abundances of the isotopes rather than just averaging out the values. Okay. It's then asking us to calculate it, so this is where we're actually going to use this data. So calculate the relative atomic mass of zinc in this sample. Okay, this is fairly straightforward. We're just going to take the relative isotopic mass and multiply it by its abundance. Okay, so we're going to do 64 times 49. And then we're going to do this for each of the isotopes and add them up. So 66, just be careful reading it. It's very easy to go, oh yeah, 64, 65. Actually, there is no 65 here. So 66 times 27.9 plus 67 times 4.3 plus 68 times 18.8. And then we're going to divide that all by 100. Okay, we're saying, essentially, if I had 100 atoms of zinc, this is how many of those atoms would be that isotope, and so on and so on and so on. And then imagine if we had those 100 atoms and we were going to take the average of them, we'd add them all up and then divide by 100, okay, if we were working out the mean. So then we're just going to calculate this. Plus 67 times 4.3 plus 68 times 18.8. Divide that by 100. Before we do that, let's just think about what sort of value are we expecting. If our isotopes are 64, 66, 67 and 68, we're expecting a value to come out somewhere between 64 and 68, otherwise we've definitely done it wrong. And given that the highest percentage abundance is the 64 isotope, we're looking for probably somewhere closer to 64 than 68. So we're looking for an answer of 65-ish probably. Okay, let's just think about whether the answer that we get is going to be sensible. 65.439, that seems reasonable. Okay, we've probably done that right. And then just check, it says give your answer to 2 decimal places. So we're not going to get away with that. We're going to have to call it 65.44. Okay, it's always worth checking. That's a silly reason to lose a mark. Okay. This question then continues. And we have some similar kind of bits here. So we've been talking about isotopes, but what do we actually mean by isotopes? Okay, isotopes are atoms, that's what they are. Okay, they're atoms of the same element with different numbers of neutrons. Okay, you could also say atoms with the same number of protons but different numbers of neutrons. That's the same thing. If atoms have the same number of protons, then they are the same element. So you could say same number of protons instead of same element here. That would be fine. Okay, but the important thing is different numbers of neutrons. Different isotopes of antimony have the same chemical properties. Explain why. Well, the chemical properties are always down to the electrons. But usually on this question, it's not quite enough just to say they've got the same number of electrons. You want to say that the isotopes have the same electron configuration. So not only do they have the same number of electrons, but they also have the same number of electrons in each shell, for example, which is kind of obvious. I mean, if they had the same number of electrons, they will have the same electron configuration, but they do tend to get a little bit picky. They want you to say this. Okay. Then it's asking us to work out the number of protons, neutrons, and electrons in this particular isotope. So we need to have a look at the periodic table. I don't know about antimony off the top of my head. So if we find antimony here, okay, you can see its atomic number is 51. So therefore it's going to have 51 protons. Okay. It's just an element. It's not an ion or anything like that. So if it has 51 protons, it's also going to have 51 electrons. Okay. And then if its mass number is 121, it must have 70 neutrons. So the protons and the neutrons adds up to 121. Okay. Right, and then we have another question here where they would give us data. This question was going to ask us to calculate the relative atomic mass again, but we've already done a question like that. So I'm not going to go through that part of the question. I've just got rid of that bit. But this is asking us to define the relative isotopic mass. Now, this is not the same thing as relative atomic mass. Okay, so you have to be really careful with reading it. They aren't quite the same thing. Okay, the relative isotopic mass is the mass of the isotope and again, it's relative isotopic mass, so it's compared to 1/12 of the mass of carbon-12. Okay, the difference here is only worth 2 marks because if it was relative atomic mass, the third mark would be for saying the weighted mean mass. Okay, we're not doing a mean if it's just the relative isotopic mass. It's just the mass of that isotope. Okay, but it is still compared to 1/12 of carbon-12.